Hello there. This morning I had woken up looking at a clock literally, and I had wondered how this converts electrical DC signal to literally time precise rotations. And it's a good combination of digital circuit concepts that we learned in electronics as well as some mechanical aspects like this gear train. Currently this is broken apart actually, but in future I will be showing the proper assembled one. So to quickly brief this thing right here, this one it is powered essentially by this 32 kilohertz crystal oscillator, and that powers literally goes into a 15-bit or 15 to 16-bit flip-flop circuitry here. And this flip-flop circuitry then divides this, and we get 1 hertz frequency somewhere around here. This is then fed to a pulse generator, which then gives it to this Levitt type stepper motor. This stepper motor is special because it converts this electrical signal to precisely 180-degree rotation. So if I quickly put it here, I've made a marking, and if I press this, notice the blue dot, it rotates literally 180 degrees per second. And so this video will be mainly about how this 180 degrees is converted to 6 degrees per second, so that we get precise 1 minute rotation. So this is the 32 kilohertz crystal, which goes to a train of around about 16 flip-flops. So as you can see, this is about 32 kilohertz going into. I'll quickly show the oscilloscope put here, and let's measure its time period. So it is precisely 60 microsecond, we can say. If we do 1 divided by 60 microsecond, it's quite literally 16 kilohertz, which is right. This divides it by 2. Now that is done all the way up to here, and thus we get 1 hertz exactly at this point. The simulation here is pretty slow. Would do a transient analysis of this by going to simulate, analysis, and transient analysis. Now here I will firstly set the output variable that I want to analyze, and it's V16. So I'll add this. I'll remove this one, and we'll set the end time to 5 seconds. Anything works honestly, as long as it's greater than 1. And let's simulate it. So this should at approximately zero point 0.5 seconds go down, and after another zero point 0.5 seconds it should come up. So we are close to zero point 0.5 as soon as this crosses, and we'll see that after some time it should, yeah. So this falling edge is seen here, and at point 1, sorry, 1 second it should come up. So this is 1 hertz exactly. And then this particular signal, I'll stop the simulation quickly. And this particular signal is actually applied to a pulse generator later on in the integrated circuit. And that pulse generator is then given to this stepper motor here. This is the Levitt type stepping motor, and it generates exactly 180 degrees per pulse, as I showed you in the physical video. So now with this part done, let's now analyze the mechanical part of how this 180 degrees is actually translated to a full 360 revolution in 1 minute. Now let's analyze the gear train that converts this 180 degree per second rotation into 6 degrees per second rotation, because 6 into 60 is 360. This is the rotor, and this particular gear, which makes 180 degrees of revolution per second, has 12 teeth. Let's just store that in memory, and let's look at what it's driving. Because the thing about gears is the amount of delay or the amount of division in rotations is obtained really by what it drives rather than just this. This also contributes, but that is main. So this is the next gear that it drives. Again, this is 12 teeth, and this is exactly 48 teeth as I counted. So notice one thing. This 12 teeth rotates once per 2 seconds. So for 2 seconds, this will rotate completely. And for this to rotate completely, let's find out how many of these rotations will be required. So dividing 48 by 12, we get 4. So once this gear rotates 4 times, then only this one revolution will be complete. And we know this rotates once per 2 seconds, so this into 2 will be 8 seconds total for this to rotate. So we can say this multiplies whatever rotation second this is by 4. This is about 8 seconds. Now, what is hidden beneath this gear is one more gear actually. So this gear is actually a compound gear which on top has 48 teeth, and on bottom actually it has 8 teeth. 7, 8. And the purpose of this is well explained when I do further calculations. So let's first this and this are the same. This is exactly this. So this gear, which is literally the second, it is attached to the second hand. Second hand has around 60 teeth, and this one has 8. So now one thing here is this and this are the same. So this rotates by 180, this will also rotate by 180. So we can say that this entire thing completes a revolution in 8 seconds. And it is driving a 60 teeth gear. So now let's see how many, to rotate this entire gear, how many revolutions of this will be required. So if we simply divide 60 by 8, we would get around, yeah, 7.5. So in order to get this one complete revolution, you have to rotate this exactly 7.5 times, which means one half cycle as well. And since this takes 8 seconds, this is effectively a 7.5 multiplier. 7.5 into 8 is nothing but 60 seconds. It means that to rotate this entire thing, you would need 60 seconds, that is 1 minute. And that is, this is essentially driving the second hand. And again, through further multiplications of such a similar kind, you get the minute hand as well as the hour hand. So if we analyze, if we conclude, that is, we can say that 180 degrees per second has been successfully translated to 6 degrees per second, which into 60 is 360 degrees. And that is essentially how a wall clock works, which is quite amazing.